Hello, everyone. I am Mitsunori Uemura of Ritsumeikan University. Let's start the third week of the Advanced Topics in Robot Control. This week begins with a continuation of the passivity-based controls we discussed last week. First, we will prove the stability of the controlled system when the passivity-based control is applied, and introduce the task space passivity-based control. Next, we will learn the history of control theory and introduce advanced passivity-based control methods. Finally, I will introduce the computed torque method. Let's first consider the significance of stability analysis of the control system. This kind of stability analysis is essential for the field of control. The reason is that a control method whose stability cannot be proved may produce unstable motions. Control systems that may become unstable are difficult to use in actual products due to safety concerns. Another important reason is that we can propose new control methods from control theory. In fact, many state-of-the-art robot controls have been inspired by past control theories. There are many other reasons, such as providing guidelines for improving control performance. Therefore, such stability analysis is essential for the field of control, and understanding the principles of stability analysis of robot control is a very important ability for engineers and researchers who are involved in robotics. Now let's see stability analysis of robot motions when we use the passivity-based control method introduced last week. In robot control, the Lyapunov function is often used to prove the stability of robot motions. The Lyapunov function is a scalar function that has a value of 0 or greater. Also, the time derivative of the Lyapunov function is 0 or less. This proves that the Lyapunov function decreases over time, and theoretically shows that the control error decreases. The Lyapunov function v, which proves the stability of the robot motions when we use passivity-based PD control, can be written like this. Here, Q is a joint angle vector representing the angle of each joint, M is the robot inertia matrix, QD is a vector representing the desired joint angle, and Kp is a feedback gain matrix regarding the angle error. This Lyapunov function is the same as the total mechanical energy when a spring and damper are attached to each joint as shown in this illustration. The first term on the right side of the Lyapunov function is the kinetic energy of the robot. The second term on the right side is the potential energy of the spring attached to each joint. Therefore, It can be understood from the physical intuition that this mechanical energy is dissipated by the damper over time and eventually becomes zero. If you don't understand these energy equations, review the mechanics. To confirm this physical principle, let's differentiate this Lyapunov function with respect to time. First, let's differentiate the term of the kinetic energy with respect to time. Kinetic energy is the multiplication of three time-dependent vector and matrix functions. Therefore, the time derivative of the kinetic energy is the sum of three multiplications of each function differentiated by time and the remaining functions as they are shown like this. Next, let's differentiate the potential energy term with respect to time. Since the feedback gain matrix Kp is constant, the time derivative of the potential energy can be calculated like this. In the formula of V dot, the first and third terms are the same. The reason is as follows. First, since the two terms are both scalars, transposing the first term does not change the value, so let's transpose the first term. The transpose of matrix or vector multiplication is the transpose of each matrix or vector after reversing the order. Therefore, the transpose of the third term is the transpose of Q dot times the transpose of M times Q2 dots. Since the inertia matrix M is symmetric, the transpose of M is the same as M. Therefore, the third term is also expressed as the transpose of Q dot times M times Q2 dot. This is the same as the first term. Similar to this, the fourth and fifth terms are the same. Therefore, let's combine the first and third terms of this equation into one, and the fourth and fifth terms into one to simplify the equation. Then, we obtain the equation like this. The first term in this equation is the sum of first and third terms of the former equation. The third term of this equation is the sum of the fourth and fifth terms of the former equation. Since all terms in this equation are multiplied transpose of Q dot from the left, let's put all terms in the curly bracket with multiplication of Q dot transposes from the left. Then we get this equation. The inside of the curly bracket are similar to the motion equation of the robot. The dimension of the inside is the same as the motion equation. Therefore, let's remember the motion equation of the robot. The motion equation of the robot can be written like this, where h is the centrifugal Coriolis term and tau is the actuator torque vector. In the case of passivity-based PD control, The actuator torque tau is designed as in this equation. Let's substitute the equation of PD control into the tau of the motion equation. Each element of the inertia matrix M and the centrifugal Coriolis term H can be written like this for the two-joint robot. Review the mechanics for specific derivation of these elements. Let's substitute this motion equation into the curly bracket of the previous equation. Then we obtain this expression. It is known that the first and second terms in the parenthesis multiplied by transpose of q dot become zero due to the characteristics of the robot dynamics. Please try actually calculating that part to check this characteristics. Because that part becomes zero, the only remaining term is the term of the transpose of q dot, kv q dot. Since kv is a diagonal matrix with positive elements, v dot is always negative. This remaining part represents the mechanical power dissipated by the joint damper. Therefore, it can be seen from this equation that the total mechanical energy V, including the potential energy artificially created by P control, decreases monotonically with time due to the artificial damper created by D control. Decreasing V means decreasing the control error Qd minus Q and the velocity of the robot Q dot. This means that the joint angle Q will reach the desired angle Qd, and that the robot will stop, and the passivity-based control achieves the control objective. Although this kind of mathematical proof is very complicated, it is very important for deep understanding of robot control and designing new control methods. The passivity-based control method utilizes the characteristic that the total mechanical energy, including the artificial potential energy created by the actuator, becomes a Lyapunov function, even though the robot has nonlinear dynamics. Next, I would like to introduce a task space passivity-based control. The PD control that I previously introduced aimed at convergence of the joint angle of the robot to the desired one. However, when we use robots in the real world, it is often the case that we want to set the desired position of the robot hand instead of setting the desired joint angle. Once the desired hand position is set, the joint angle that realizes the hand position can be obtained by inverse kinematics. However, solving inverse kinematics may not be easy if the robot has much degrees of freedom. Therefore, it would be convenient if we can control the robot directly from the desired hand position without solving the inverse kinematics. Such direct control from the desired hand position is called task space control. In the task space passivity-based control, task space control is realized by considering an artificial spring attached between the desired hand position and the actual hand position of the robot as shown in this illustration. As with the previous case, the artificial dampers create damping torques at each joint. Similar to the case of considering the joint spring, we can imagine that the robot hand moves toward the desired position, and the mechanical energy is dissipated until the spring energy is exhausted. When we use the task space passivity-based control, the actuator torque vector tau is expressed by this equation, where J is the Jacobian matrix that represents the relation between the joint velocity vector q dot and the hand velocity vector x dot, which is the time derivative of the robot hand position vector x, and Kp is the diagonal matrix that represents the spring stiffness. In this equation, Kp times xt minus x is the force vector that represents the spring force exerted on the robot hand. As we learned in the analytical mechanics, the transpose of the Jacobian matrix J converts the hand force into the joint torque. Therefore, this first term is the torque applied to each joint of the robot from the task space spring. The kVq dot in the second term is the same as in the previous case, the torque acting on each joint by the artificial damper. As shown in these equations, task space passivity-based control has the advantages that it does not require inverse kinematics nor detail parameters of the robot. It also has the advantage that the computational cost for computing these equations is very low and that task space passivity-based control can be easily implemented. Now, in order to understand this control method more deeply and clearly, let's actually implement task space passivity-based control in a simulation using MATLAB and Simulink. I will not explain the details of the program this time. In the simulation, let's display the hand position of the robot in a graph to check the time history of it. Creating this simulation is homework for this week. So let's take a few minutes and create a simulation. Here, I would like to analyze the stability of motion when using task space passivity-based control. Therefore, as in the case of passivity-based PD control, the total mechanical energy of the robot, including the potential energy of the task space artificial spring, is defined as the Lyapunov function V shown in this equation. The potential energy of the task space spring can be written by the second term on the right side of this equation. By differentiating this Lyapunov function with respect to time, we obtain this equation, and the mechanical energy is dissipated by the artificial damper. Therefore, it was shown that task space passivity-based control can also guarantee the stability of the controlled system. Let's specifically calculate the V by yourself. Before we get into the next control method, I would like to introduce the history of control theory to clarify the historical position of robot control. Classical control theory based on the analysis of transfer functions was established around 1950 to 1960. Classical control theory has the advantage that the frequency characteristics of a system can be finely designed by frequency analysis of the transfer function. However, classical control theory has the big disadvantage that it can only be applied to linear systems with single input and single output. Modern control theory, established between 1960 and 1980, has overcome this disadvantage. Since modern control theory is based on a state space model using linear algebra, we can apply it to linear systems with multiple inputs and multiple outputs. Separately from these theories, nonlinear control theory began to be studied around 1920. Nonlinear control theory deals with nonlinear systems that have multiple inputs and multiple outputs. A nonlinear system is a system that has characteristics that cannot be represented by a linear state space model. The characteristics of any systems in the world can be formulated as a nonlinear system. In other words, while classical control theory and modern control theory deal only with systems with specific properties, nonlinear control deals with any systems. Therefore, nonlinear control theory is theoretically very difficult and is still in growth. Therefore, there are still many challenges. The theory of robot control started around 1960. The motion equation of robots are nonlinear and cannot be treated by modern control theory. However, because robot dynamics does not have extreme complexities, we don't need nonlinear control theory to control robots. Therefore, the theory of robot control has produced unique control that is different from other control theories, and even influences nonlinear control theory. In fact, passivity-based control theory is a unique control that has many advantages by using the energy conservation law of the motion equation of robots, and has been generalized and extended in nonlinear control theory. The control methods, which will be introduced later in this class, are also unique methods, and robot control theory is a very interesting research field that establishes one theoretical framework. In order to understand the position of each control theory more intuitively, I would like to show the conceptual diagram of each control theory. First of all, the nonlinear system can represent any control systems in the world, and I would like to draw it with a big blue circle like this. The linear system with multiple inputs and multiple outputs that we deal with in modern control theory is a part of any control systems, and thus can be represented by a small circle in the blue region. However, note that this circle is small but has a large meaning, because all nonlinear systems can be regarded as linear systems when they are considered in neighborhood of a certain state. The linear system with single input and single output handled by classical control theory is part of the more general linear system handled by modern control theory, and thus can be represented by a smaller circle contained in the green region. Since robots have nonlinear motion equations, they are not linear systems. On the other hand, since robots are specific nonlinear systems, they are part of the nonlinear systems. Therefore, robots can be represented by a small circle that occupies part of a blue circle. However, since the motion equations of robots can also be linearized around neighborhood of a certain state, robots include some green areas. As seen this, robot control theory is a part of nonlinear control theory, but it is a very interesting and unique theoretical framework. This visual confirmation of theoretical positioning will give you a more intuitive understanding of what you will be learning in this class. Next, I would like to introduce some advanced passivity-based control. First, I would like to introduce control of grasping and manipulating an object by a robot hand. When a robotic hand grasps an object, the motion equation of the entire system that includes mechanical constraints has a very complex structure. Moreover, when grasping various objects, to obtain accurate information about the objects is not easy. For such a system, it is not easy to apply control that uses detailed information about the controlled system. In fact, Few control methods have allowed actual robotic hands to grasp and manipulate objects before the passivity-based grasping control method was proposed. On the other hand, the passivity-based grasping control method utilizes the advantage that it does not use the detail information of the grasped object, and various objects can be grasped and manipulated with simple control without using the object information. Because of these advantages, this related work has won several academic awards at important international conferences in the field of robotics. Passivity-based control of humanoid robots, which also takes advantage of passivity-based control, does not require huge computations, has also won an academic award at an important international conference. When we use commonly used computed torque method for a robot with a large number of degrees of freedom such as a humanoid, huge numerical calculations are required. This causes problems such as the need for a large computer and the inability to use the computer for other processing. To the contrary, passivity-based control requires only small computational cost, and such a problem can be solved. Passivity-based control, which automatically optimizes the stiffness of the spring to minimize energy consumption, has also been proposed for periodic robot motions. Using this method, it has been confirmed that periodic motion like this movie can be generated with about 20 times better energy efficiency compared to the case without this method. This method also does not use huge calculations and does not use detailed information on the controlled object. Therefore, we plan to contribute to improving the motion performance and energy saving of walking robots and walking assist robots in the future. That concludes the introduction of passivity-based control. Next, I would like to introduce the computed torque method. As the name implies, the computed torque method calculates the feed-forward torque required to generate a desired motion. Since the computed torque method is mainly used for CP control, the desired motion is a time-dependent function q dt. In order to understand the principle of the control method as easily as possible, I introduce the principle of the computed torque method using the simplest example shown in this figure. The motion equation of this robot can be expressed by this very simple equation. First, let's define the control objective. In the computed torque method, the desired motion qd depends on time, and its time derivative qd dot d is the desired joint angular velocity, and its time derivative qd2 dot d is the desired joint angular acceleration. Therefore, the control objective is to let the joint angle Q of the robot follow the desired angle QD. Then, the robot joint velocity q dot and joint angular acceleration q2 dot should also converge to the desired velocity qd dot and acceleration qd2 dot. The feed-forward torque tau d required to achieve this desired acceleration can be calculated as I bar qd2 dot by substituting qd2 dot into q2 dots in the robot motion equation. In fact, when this tau d is substituted into the tau of the motion equation of the robot, dividing both sides by I bar results in q2 dot equal qd2 dot. This means realization of acceleration tracking, which is one of the control objective. However, since this feed-forward torque alone does not achieve the control objective of the joint angle and angular velocity, error feedback related to joint angle and velocity is added as in this equation. These feedback terms are composed of the tracking error with feedback gains, and then similar to those of passivity-based control. Due to the effect of the feedback, the joint angle and velocity will also converge to the desired ones. The above is the basic control design of the computed torque method. You can find that the feedback part is similar to passivity-based control, and the feed-forward part calculates the necessary torque from the motion equation of the robot. To understand the above more clearly, let's implement the computed torque method and the simulation of the one-joint robot on MATLAB. Again, I don't explain details of the simulation. First, define the desired angle, angular velocity, and angular acceleration with a time function using some functions, such as trigonometric function, a polynomial, and so on, and change the actuator torque formula to that of the computed torque method. When you use the value of the time in MATLAB function, paste the clock block into the model from the sources in the library browser. The output of the clock block should be connected to the input of the controller block as time t. When displaying the simulation results, make sure that both the desired motion and the actual motion are displayed, and check whether the actual motion converges to the target motion. This exercise is also homework today. So let's take a few minutes and create a simulation. Now, at the end of today's class, let's prove the stability of motion when we use the computed torque method in the simplest example. In the case of the computed torque method, the tracking error between the actual joint angle and the desired 1qd minus q and the velocity error between the actual joint velocity and the desired 1qd dot minus q dot should converge to zero vectors to realize the control objective. Therefore, we define the Lyapunov function v using the squares of these errors like this. Let's differentiate this function v with respect to time. Then v dot becomes like this equation. Next, let's substitute the actuator torque of the control law into the motion equation, and substitute the motion equation into IQ2 dot of the equation of v dot. Then we obtain this equation. The definition of tau d was I bar q d2 dot, and then cancel the first and second terms in the first parentheses of this equation. The term relating to the third term in the same parenthesis cancels with the last term in the whole equation. Then, all remaining term in this equation is the term of the fourth term in the first parenthesis. After all, v dot is always smaller than 0, because the square of qd dot minus q dot is always greater than 0. Therefore, it was proved that v decreased monotonically with the time t. This proves mathematically that the tracking error decreases with time and the control objective is achieved. Finally, I would like to introduce homework for this week. This week's homework is to create the MATLAB simulation I described this week and submit it as a report. In the report, please include the figure of the simulation model of Simulink, the program source of the robot dynamics block, the program source of the controller block, the simulation result graph, and the explanation of the simulation contents and the simulation result. Please submit the created report through Manabar. That concludes this week's class. Thank you for your hard work.